Hi everyone, so today we'll be solving this dynamic programming problem together. So this problem is about an airplane trying to fly between airports. We have n equally spaced airports in a line, and airport I charges a takeoff fee given by fee I, where fee is just an array of numbers that's given to us. And the plane can fly at most 2 cities forward before it has to stop to refuel. So, for example, a plane currently at City 5 can only fly non-stop to City 6 or City 7, but cannot fly to City 8, or any city beyond that. So the question that we'd like to answer is, what is the minimum possible total takeoff cost of flying from City 1 to City N? So, since it's a dynamic programming problem, we always start by defining subproblems. And of course, before we can define the subproblems, we should figure out what the subproblems should be, which is always possibly one of the hardest parts of a dynamic programming problem. But a common tactic for doing this, for defining subproblems, is to ask ourselves, what is the answer if we only look at a prefix of the problem? Of course, there are other common tactics which we may go over in future videos, but the reason I chose this problem is because it introduces this common tactic, which is also one of the simplest ones. So again, the tactic is asking ourselves, what is the answer if we only look at a prefix of the problem? Now, what does that mean in this situation? What is a prefix of this problem? Well, for flying all the way to City N, maybe a natural prefix is that we don't have to fly all the way to City N. Maybe we can only complete part of our journey and ask ourselves, what is the minimum possible cost of flying from City 1 to City I, where City I is some city in between City 1 and City N. So let me just write that down. We can define our subproblem as min cost I will be the minimum cost to arrive at City I, starting from City 1. And we need to make sure that we can actually obtain our final answer from our subproblems. In this problem, that's pretty straightforward, because our final answer will just be min cost of n, because according to our definition, that's the minimum cost to arrive in City N, which is exactly what the problem is asking for. So, now that we've finished with defining our subproblems, the next step of a dynamic programming problem is always to write out a recursive definition for our subproblem. So, you may be wondering how to do that, and again, there are common themes or common tactics or common lines of thinking that always come up. And when we're thinking about this problem, it may seem overwhelming at first. There are so many different ways to hop or leapfrog from City 1 to City N. So many choices. How can we think about and analyze all of them? Well, instead of dealing with so many choices, we should limit the scope of what we're thinking about and just focus on a single choice. So, when we're thinking about recursive definitions, a common tactic or a theme that always helps is to focus on a single choice. Now, what is the choice that we're focusing on in this problem? Well, we can think about what the last flight we took was to get to City I. So, let's think maybe we're in City I right now, and then to the right there's City I plus 1, and so on, and to the left we had City I minus 1, I minus 2. Maybe a bit further left, we have city I minus 3. And then now, we want to ask ourselves, what's the minimum possible cost to arrive at city I? And then, what's the choice that we're going to think about? Well, the choice can be, what was the last flight that we took in order to arrive at city I? And if we think about this, and we also factor in the restriction that plane can fly forward at most 2 cities, then we'll see that the last flight either would have been flying from city I minus 1 to I, or from city I minus 2 to I. So now that we've focused on a single choice, we can define this choice based on the subproblems. So what would happen if we flew from city I minus 1 to I? Well, in order to fly from city I minus 1 to I, we would have to first arrive in city I minus 1. So starting from city 1, which is way back when, we would have to take some path to arrive at city I minus 1. And then after we take this path, we then take one more flight from city I minus 1 to I to make it the rest of the way. Well, how much is it going to cost to take this path? This is where we can look to a smaller subproblem to provide us with an answer. Because we need to arrive at city I minus 1, and the cheapest way to do that is min cost I minus 1. And then once we've arrived at city I minus 1, we need to pay the takeoff fee for city I minus 1 to take off from city I minus 1 and make this last flight to city I. Similarly, the other choice would be to first go to city I minus 2 somehow from city 1, going on some path, and that would require min cost I minus 2 to arrive there. Then, once we've arrived at city I minus 2, we need to pay the takeoff cost of city I minus 2 in order to take the last flight to city I. Since we're trying to find the minimum possible cost of flying from city 1 to city N, from city 1 to city N, the way that we compile our choices is we look at all our choices and find out which one's the best choice. And the one that's the best choice is the one that gives us the least cost. Since we have 2 choices, that just involves taking the minimum of 2 possibilities. So we have min cost I equals the minimum of 2 possibilities. We could have either first flown to city I minus 1 and then taken one last flight, which costs min cost I minus 1 plus the cost of taking off the last time. Or we could have gone to city I minus 2, which would have required cost of min cost I minus 2, and then taken off from city I minus 2 to arrive at city I. Whenever we're doing a recursive definition, just a small detail that is really important not to forget about is the base case. So let's just do the base case real quick. In this problem, the base cases are min cost of 1, or the minimum cost just to arrive at city 1. Since we started at city 1, it doesn't cost anything to get there, so that's just 0. And then min cost of 2. For min cost of 2, we don't have a choice of how to get to city 2. We have to fly from city 1 to city 2. And the cost of doing that is just taking off from city 1. So that will be cost 1. Then for 3 on upwards, we can just use this recursive formula to calculate the min cost of arriving at city 3, 4, 5, 6, 7, so on, all the way up to n. So now that we've finished the second step, third step is to figure out what order we're going to evaluate the recursive definition in. And the way that we decide this is that we look at the dependencies. So for example, min cost I depends on min cost I minus 1 and I minus 2. And since it does depend on those two, we need to make sure that min cost I minus 1 and min cost I minus 2 are evaluated before we try to evaluate min cost I. So the way to do this is we could either evaluate I going from down upwards, so first evaluate I equals 1, 2, 3, all the way up to n, or we can evaluate starting I equals n, then n minus 1, n minus 2, and so on all the way down to 1. If you think about both possibilities, you'll see that going from 1 up to n allows us to have the dependencies evaluated before the min cost I, which depends on these two. Whereas going the other way, we'll be trying to evaluate this before we've even evaluated these two, which is not possible. So our evaluation order is I goes from 1 up to n. Cool. Then we need to write some pseudocode for this problem. And usually once we have this recursive definition and evaluation order figured out, the pseudocode isn't a huge deal. So maybe we can have get min cost, and then as an input we can take in this fee array. And then first, we can initialize the data structure that we're going to use to remember these subproblems. And here it makes sense just to use an array. So we're initializing an array just to store all of the answers to our subproblems, which allows us not to recompute them. Once we've initialized the array, usually the next step is to fill in the base cases. So we have min cost 1, and then assign 0 to that, and then min cost 2. Alright, I realized I wrote the wrong thing here. This should actually be fee, because that's what the array is called. And same here, I wrote the wrong thing. Anyway, then min cost 2 will be initialized to fee 1. Next we can just implement our recursive definition. So for I starting from 3 up to n, we have min cost I equals the min of these two things. Alright, these should be square brackets because we're storing the results in an array and it's no longer calling a function recursively anymore. And I apologize for the handwriting becoming progressively more slanted and unneat throughout the video. Now that we've evaluated this for loop, remember that our final answer is simply min cost n. So we just need to return that. And we're done with our pseudocode. Remember now, the final step in the dynamic programming problem is to analyze the runtime of the algorithm. So what is the runtime of our algorithm? Well, first initialize an array with n elements this step takes O of n. Then for base cases, filling them in just takes O of 1. And then we have this for loop where we do something for every element from 3 up to n. And then each of these computations takes O of 1 because we're just taking the minimum of 2 things. And then since we're doing a for loop over n elements and the inside takes O of 1, this in total takes O of n. And then we just return min cost n. So we have O of n, O of 1, O of 1, and O of n for the for loop. So in total, our runtime is big O of n. And we're done.